All right, hello everybody. Welcome back to M155 mathematical modeling. In this lesson, we're moving into something called statistical studies, things that deal with sampling and bias. When we see a statistic reported in the media, in research, or social media, one of the first questions that you must ask yourself is, where did the data come from? You shouldn't just blindly believe it just because it comes from, you know, Penn State or USC or any other predominantly white institution, or even CNN, NBC. It doesn't matter that these people put out statistics. What matters is, where did the data come from? Okay. Always question it, no matter who it is. Where did the data come from? What data are you using? What data was considered, what data was not considered, because that's the only way that you're going to actually understand statistics, is by asking these thoughtful questions. Okay, a number can be calculated correctly, right? They're like, oh well, the numbers are this. It's not debatable, it's a fact. You've heard it before in your entire life. But anybody can put numbers together and add them up and subtract them. But the question is, do they produce a misleading conclusion if the data were collected poorly? And when I say collected poorly, I mean not taking in consideration all things and making it seem as though you are. Okay. So I do want to begin with some terminology. We have population. So the full group a study seeks to describe. Sample, which is a subset. It's kind of like this would be the sample, and this would be the actual population. For example, the population of all students at the university versus the population of girls, or excuse me, the population of young women, or the population of young men, or the population of demographics, what age group, how old are you, whether or not you're a local student, whether or not you're an out-of-state student. These are samples of a particular population. And then you have random sample, is a sample selected by chance, such as, drawing in a box and pulling out some information. All right. Usually it's represented by n. So a sample is usually represented by n in a statistical study. We typically use small n. So we typically use small n and big N to represent population, and to represent the subset, or the smaller number, we use small n. A random sample is a sample that's selected by chance. And then you have bias, that's obviously a systematic distortion of how data is collected or analyzed. And yes, bias is very systematic. Okay, you look at the media, you see, well, crime is mostly being populated that black people are committing the most crimes, but that's called systematic distortion. So they're actually distorting reality to make you think that black Americans are contributing to the most crime, when we are actually the least criminals in the country, based on real per capita statistics. Confounding occurs when the effect of one explanatory value variable becomes mixed with efforts of another factor. Okay, all right, and we're going to get into this in this particular lesson today. So we have example one. Suppose a university surveys 600 randomly selected students about food insecurity. Let's identify the major components. So first of all, population. Okay, the population is the full group that the university wants to describe. Okay, assuming that the university wants information about its students, the population is all students at the university. So the population will be all students at the university. And we could represent the population size as n. N equals the total number of university students. Okay, so capital N could be the total number of university students. Okay. Next, we have sample. So a sample consists of the students actually being surveyed. So N would be 600, right? So students surveyed, right? In this study, a a variable, right? A variable is the characteristic being measured for each student, right? So we're looking for variable then statistic. So in this study, that would involve the students' responses concerning food insecurity, right? So the variable would be the student responses, okay? And then finally, the statistic. A statistic is a numerical summary calculated from the sample. So for example, I'm going to just call it the stat for short. So for example, X would be equal to the number of sample students reporting food insecurity. Then the sample portion would be essentially P times, or excuse me, let's see, it would be P equals X divided by N, because N would be the students surveyed, right? So N would be the students surveyed, but X, let's say X would be the number of sample students who reported in the affirmative of food insecurity. So I'm going to say affirming. Okay. So those who are affirming insecurity, we could calculate the population, or the small p, meaning, so the small p would be equal to those affirming food insecurity out of those who are actually surveyed. And so since n is equal to 600, that would be E is equal to X divided by 600. So notice that we have not been told the value of X. So we cannot necessarily calculate the actual sample portion, but we can identify how that statistic would be calculated. So again, remember, population is the entire group or all students. The sample is the observed subset, in this case, the students who were surveyed. The variable is the characteristic being measured, and so in this case, that would be the student responses. Who is affirming, who is affirming or not affirming food insecurity? The statistic would be if we said, okay, well, we want to calculate this group and say, well, we're going to call them X, and we're going to say how many are those who affirmed food security, and then we can calculate the percentage of those by taking X, dividing it by those who are surveyed, and then let's just say we wanted to say Y was those who didn't affirm food insecurity, so that would be Y divided by 600. Okay, that's how we develop a statistic. All right, let's continue. Example number 2. Suppose a university conducts a survey about campus parking, but the survey is contributed only to students who own cars. Is that a problem? Absolutely. Yes, this is a problem. So the reason why this is a problem is students who own cars are not necessarily representative of all students. There are students who walk, students who ride bikes. Okay. So there's some who walk, ride bikes, scooters. I mean, maybe even public transportation, right? Maybe they live on campus, depending upon some, excuse me, depend, or even they may depend on someone else. They may carpool for transportation. They may have very different opinions about, those groups may have very different opinions about parking policies, right? Well, they're like, well, I really don't care because I don't have my own car, or you know what I mean? So they're gonna have a biased opinion, and by bias doesn't necessarily mean something negative, right? The selection process has essentially systematically excluded those groups who whose experiences matter, but whose experiences cannot be calculated systematically in the study. So this is called a selection bias. Okay, because how can you survey a campus um, about parking, and it's distributed only to students who own cars? Well, what about all the other students? You know what I mean? What about those students, right? So that's systematic bias. The problem is not going to be their arithmetic. The problem is actually before the arithmetic ever began. All right, so pause and try problem. Consider the following survey question. Do you support the wasteful proposal? Think about the wording, right? The word wasteful already gives you a negative characteristic of this proposal. Do you support the wasteful proposal? Brother, sister, why are you framing it like that? You know what I mean? So like if you're ever in a public setting where someone phrases their question this way, do you support the wasteful proposal? Well, why are you calling it wasteful? That would be your first question. It shouldn't be you ready to answer this question, or it shouldn't be, you on the fence of the question. You should say, well, what do you mean by wasteful proposal? And then make them be on the defense of explaining what that term actually means, because you have to actually compare that with something more neutral, such as, do you support or oppose the proposal? Okay. So that would be a more, do you support or oppose the proposal? Okay. So again, the wording wasteful already gives you a negative characteristic of the proposal. You have to compare this with something more neutral. Okay. This is a more neutral response. The first question is going to influence people before you're actually ever being able to answer the question. So this is an example of even wording bias. Like, why are you wording it this way? If we let P equal, you know, the true proportion of the population who support the proposal, then our goal is for our survey to actually estimate P to give us useful information about P, right? So then we would be able to differentiate. But if the wording already pushes people towards a conclusion, right? Do you support the wasteful proposal? Because then if there's, think about if you answer yes to this, well, they're going to be like, well, they're going to mock you, and they're going to mock you on the basis of this one word, right? So you got to be very careful. Good statisticians design tries to collect information without trying to sway people. This is what a good statistician is. Do you support or oppose the proposal? This is a terrible statistician, or just a terrible, maybe even a terrible character person too. Do you support the wasteful proposal? Right? Let's continue. Example number 3. Now, suppose we're studying whether a tutoring program improves a student's performance, right? Um, study numbers. A study randomly assigns students to participate in a tutoring program, right? And then study number 2, that's study number 1, a study randomly assigns a tutoring program, and then another one compares volunteers. So they're number 2 simply is comparing students who voluntarily choose tutoring with students who did not. Okay, so which study provides stronger evidence for a causal or a causal conclusion? The randomized experiment does. Okay, so a study randomly assigning a tutoring program, right? We'll call that one A, and then we'll call this one B. So another one is compares volunteers. Okay, in reality, the randomized one does. Okay, explain which better supports a a a causal conclusion. Okay, the question though is why? Well, because random assignment helps balance other characteristics between groups, right? So in the voluntary study, the tutoring students may already differ from the other students. For example, perhaps students who voluntarily attend tutoring are more motivated, right? So the students who, you know, who voluntarily attend, they may be more motivated, right? If you go to tutoring, if you meet with your professor, if you're tracking on all your work, you watch your videos um before you come to class to ask questions to get more understanding, things like that. Well, those students are going to be different from those other students, right? They have more of concern. They're more concerned, they're more motivated. They're more willing to ask for help, right? So those who voluntarily attend tutoring, they may be more motivated, they may be more concerned, they may be more willing to ask, or studying more hours outside of the tutoring program. Now, tutoring tutoring is essentially mixed together with these factors, right? Because just because like you voluntarily attend doesn't mean you're more motivated, more concerned, or necessarily more willing to ask for help. You might just be like, well, I don't want to lose my scholarship, or I don't want to, make a failing grade, and so you might be doing those things out of like just necessity, like, hey, I have to do this because I want to make my life better. So it might be something other than the ones that I'm just mentioning, right? So change in outcome is the same as, like an effective tutoring or maybe even other factors. Okay. So we have to take that into consideration. Okay. All right. Let's move on to example number 4. Plan A. So consider two sampling plans. We got plan A, select every 10th name from the full roster, the university roster. And then we have plan B, which is surveying students from one resident hall. Okay. Which is more likely to represent the university as a whole? So generally plan A, right? Okay. Plan A draws students throughout the university roster, right? Plan B takes students from, one geographic location. There's one resident hall, right? So this is not going to be very demonstrative of the entire university population versus plan A, which is going to represent the broader university roster. Okay. Whereas plan B takes from one geographic location. All right. So I'll give you an example. Student living in resident hall may share characteristics that differ from just the overall population. For example, they might have, this may be a freshman dorm or a freshman hall, right? Um, so freshman hall, age is going to be a factor. They're going to be younger. Um, let's see. They may have they might be on meal plans, right? They may not, necessarily pay for their own food or other characteristics. So this is not going to be very representative of, say, taking every 10th person from the full roster across the university, right? So with plan A, we would still want that roster order and the starting point to avoid something like systematic bias. Okay, but still, Plan A would be more representative of taking the whole rather than a part of the university structure. Okay, common mistake. This is one of the most important ideas in the entire lesson. Suppose an online poll receives um, 200,000 responses, right? That's an enormous sample. Does that automatically mean that the result is trustworthy just because you got a lot of respondents? No, the answer is no. So, first of all, a biased online, it already telling you that it's biased, but we don't know that. But we're saying that, you know, wise sample size cannot fix a defective selection method. Well, just having a large number doesn't mean it's trustworthy. Okay, that's very important because sometimes I was like, oh well, we got 200,000 people to participate in the survey. Okay, well 200,000 people with, what are the demographics? What are the contextual factors of those students? Their age group, variables, ethnicity, things like that. Those things matter. Okay, so again, suppose the website's audience, heavily favored one side of the issue, right? Let's just say, you know, with respect to should we go to war with another country, and then let's just say, all of these are Republicans, right? And let's just say all the Republicans are like, yeah, let's go to war. Well, this is going to be a favorable survey in one position. It's not going to be in the other position. So we got to be very careful when we think about, large samples with respect to whether or not this actually makes sense. Okay. So let's summarize this statistical studies looking at samples and bias. So again, population would be the full group. The sample would be the group that you are observing, and we often represent them as a capital N, lowercase n. A random sample uses a chance process to select observations. So if you have a random sample, you're leaving it up to chance. All right, well, I'm gonna reach in this bucket and I'm gonna pull out names, and the names that I pull out, you guys are gonna present first. That's a random sample. Okay, it leaves it up to chance. It doesn't. You're not influencing who's gonna be pre-selected. Um, bias. Bias is a systematic distortion. It's a refusal to take into consideration the variables of your statistical sample. And people do it all the time, which is why you have to ask the question, where did the data come from? Who presented the data? Where what information is being included and what information is being excluded. Okay. All right, that concludes this lesson, and thank you again for watching, and I'll see you in the next one.